graph theory, right. So, we have seen lot of different data structures, that stacks, queues and linked list. I said that these three are linear data structures, okay. And we have non-linear data structures. In that we have trees. We have studied about trees, which is a non-linear data structure, okay, which is a non-linear data structure, right. So, another data structure what we have in non-linear data structures is graphs, okay. So, practically speaking, in solving, see, where do we use these data structures? We use these data structures in almost every problem of our computer science. You take any generic problem, any general problem you take, that you will try to frame it as a program, right. When you frame it as a program, you will be using some data structure to store the data, okay. Suppose you are building, you are trying to construct one software, okay, for ticket issuing. You are conducting some event in your university and you want to build one software for ticket issuing. So, you will be using queue data structure there. Whoever comes first will be given the first serial number or first seat, kind of, right. So, depending on the problem context, you will be choosing some different data structure, right. So, you know already about these four, when and where we use these data structures, right. So, graphs is one very popular data structure which has wide application compared to all these four, okay. Compared to stacks, queues, linked list and trees, graphs has very much applications in solving real time problems or real life problems, okay, using programming, right. So, this is also a non-linear data structure. It means data is not in a sequence, it is not stored in sequence, it follows some random pattern to store the data, okay, right. So, let us go deeper into this graphs. Let us understand the terminology of graph theory, right. So, a graph is a pair V comma E, where V is a set of nodes called vertices and E is a, this is again E is a collection of pairs of vertices called edges, okay. So, a graph contains nodes. If you see your tree structure here, okay. So, actually we have to study graph theory first, then we have to go for trees, okay. I will quickly compare this graph with the trees. So, we know that this is a tree, we know that this is a tree structure, right. This is node 1, this is node 2 and node 3, we are calling this as a tree, okay. Actually tree is derived from a graph, right. So, a graph looks something like this. So, what is definition of tree from graphs? If I say tree is a graph, without any cycles, See here, this is node 1, this is node 2, node 3, there is a cycle here 1, 2, 3. It means if you are starting at 1, you can travel to 2, travel to 3 and come back to 1 again. So, we say there is a cycle. So, any graph which does not have a cycle is called a tree. So, tree is derived from this graph data structure, okay, from this graph data structure, right. So, we are saying that graph is a pair vertices comma edges, where V contains the vertices A, B and C and E contains the edges like this A comma B, B comma C and C comma A. So, a graph is a pair V comma E, where V is a set of vertices and E is a collection of pair of vertices called as edges. So, it is like this, vertices is given, edges is given. With this you can construct a graph. How? Here A comma B means there is a path from A to B, B comma C means there is a path from B to C, C comma A means there is a path from C to A. So, this is your graph. So, number of vertices is given by V and the edge formation is given by the set E, right. And next, directed edge. So, between two nodes, okay, you can have a directed edge. If there is a link between two nodes which contains arrow mark, it is called a directed edge, okay, it is called a directed edge. Next, undirected edge, right. Undirected means there is no direction, it is both two ways, it is two ways, this is only one way, this is only one way. See, one way road traffic is an example of directed edge. Okay, undirected means railway lines, in the same track train can go and train can come, both are possible, right. So these are two different concepts, directed edge and undirected edge. Let us see. So directed edge is something which has a direction, and undirected edge it has no direction. Then directed graph, a graph which has directed edges is called directed graph, something like this. Okay, from A to D I have a path, C to D I have a path, C to A I have a path, like this. Undirected graph is something like this, there is no direction, it can go from this way or this way, two-way traffic is allowed. Then a graph with no cycles is called a tree. So this is a tree, it has no cycles, it is a tree, right. So tree is a acyclic connected graph. Then a self loop is an edge that connects to vertex itself. So in a graph I have something like this, C and I have D, right. I have a small graph, if it is connecting to itself, this is called self loop, and two edges are called parallel. Two edges are parallel if they connect the same pair of vertices like this, AB. Next, degree of a vertex, right. So given a graph, for example, you have something like this, right. What is degree of a vertex? Degree is number of edges incident on it. So for this node A, the degree will be 1, 2, 3, 4, 5. Total 5 edges are incident on this vertex A. That is the degree. Then here 1, 2, 3. Here also 1, 2, 3. 1, 2, 3. And here it is 2. So the degree means number of edges connecting to that vertex, okay, is called your degree. Next, subgraph. Okay, so given a graph, if you are removing some certain number of edges, okay, it is a subset of a graph's edges that form a graph. So this, in this case, if this is a graph, I say, if you remove one subgraph for this will be, I have A, I have D, I have B, right. This could be one subgraph, this is one subgraph. Removal of a vertex, right, this is one subgraph of this graph. Another subgraph will be B to C to D, this is another subgraph. Okay, like this we can have n number of subgraphs in a given graph. So it means it is subset, the vertex set and edge set, this is subset of this original graph G, right. So a path in a graph is a sequence of adjacent vertices. Okay, see here there is a path from G to C, C to D, D to E. So to have a path from G to E, right, these are all the adjacent vertices from G to E, G to C because this is adjacent to G, then to D, these two are adjacent, then to E, then to F. Okay, like this I can have the path. A path in a graph is a sequence of adjacent vertices, adjacent, right. Cycle. So a cycle is a path where the first and last vertices are same. If you begin at this point, you travel back and come back to the same place. Okay, this is a cycle. We say that one vertex is connected to another if there is a path that contains both of them. Okay, a vertex is called connected if there is a path containing both of them, like this, right. Next, this is disconnected components, this is disconnected graphs. We can say this and this are disconnected because there is no edge between these two set of vertices, there is no edge between C and D, C and A, this does not exist. Then we say these are disconnected. And the very important one is directed acyclic graph, DAG. What is directed acyclic graph? A graph without any cycles. A directed graph without any cycles is called directed acyclic graph. See here there is no cycle. From A it is coming to D, from C it is coming to D, and from C it is going to A. So, there is no cycle here. I am starting from C, I go here, I come back, but I cannot come back to C again. Same is the case for B as well. See, from A to B I can go, but B to C I cannot come. C to A to B I can go, from B to C I cannot come. So, there is no cycle. So, directed acyclic graph is a directed graph with no cycles. Next, these are all few graph terminologies which will be covering quickly. Right, a forest is a disjoint set of trees. Okay, so many trees together, like this one tree. Disjoint means they are not joined together, but they are there is no connection between those. All these set of trees is called a forest. What is a spanning tree? Spanning tree of a connected graph is a subgraph that contains all graph vertices and is a single tree. Okay, so given a graph like this, what is spanning tree? So let us take this. I have a graph G like this. This is A, B, C and D. Spanning tree, from this graph generate a tree such that all 4 nodes exist, all 4 nodes should exist, and it should be a tree. It should be a tree means there should not be any cycles. That way you should have. So, one answer for this can be, if I can connect this way, this is a tree. Okay. Spanning tree means from a given graph find out a tree such that all vertices should exist. Okay. So, this is one graph. Other example could be, I have 4 vertices like this, this is also one example. Another one, if I have something like this, this is also one example. All these are spanning trees. Okay. What is spanning? Forest of a graph is the union of spanning trees. The union of this together is called spanning forest. Next, bipartite graph. What is this bipartite graph? Given a graph, right, if you can know, suppose let me take an example. See, I am having this is a graph with me. Okay, there is a cycle also. So, this is A, B, C, D, E, F, G, H. What is bipartite graph? If you can partition this, what are the vertices you tell? Vertex set contains A, B, C, D, E, F, G and H. Oh sorry, yes, A, B, C, D, F, G, H. This is my vertex set. Is there any possibility to partition this vertex set into 2 different set of vertices? Such that, is there any possibility to partition this set of vertices into 2 sets such that there is at least one edge between any one of these vertices to any one of these vertices? Can we do that? Yes, we can take A, B, G, H as one set, then C, D, F, E as another set. Why? There is a path from B to C, there is a path from G to F. So, at least there is a vertex from any one of this element here to any one of this element here. Then we call it as bipartite graph. This graph is bipartite graph because we can partition this graph into 2. Or 2 different sets of vertices such that there is at least one edge between any one of them to any one of this. Next, weighted graph. Okay. What is weighted graph? Sometimes in graph we may have to have some weight. This weight might represent the distance, it might represent the time, it might represent the money. Okay. So, assume this is you are a this place, you are here, you have to travel to this G. You are traveling from city 1 to city 2. There are different paths to reach from city 1 to city 2, right. This indicates the time taken to reach in one instance. First one, I can assume this as a time. So, this tells us that from A to D it takes 5 minutes, from D to F it takes 6 minutes, from F to G it takes 11 minutes. So, how much time it takes from A to G? If I take this path, 11 plus 11, 22 minutes it may take, for example. Okay, you can say minutes or hours, whatever is our choice. Is there any other way? If I can take A to C, then C to E and then come here, 14 plus 9, this is 23, this is large again, right. So, you like this weighted graph, sometimes you have a on a edge there will be a number, that is the weight might indicate time. Second one, money. Okay, second one is money. So, you have to reach from city A to city E, you have to reach from city A to city E. How do you reach in less cost? How do you reach in less money? So, this is 5 rupees or maybe you can say 500 rupees from A to D. So, if you take this path and this path, it is 20 rupees, 15 plus 5, right. But if I take this 7 plus 7, it is 14 rupees, right. So, like this number on an edge indicates the weight, okay, which can represent either the distance or time or cost, etc. So, any graph which contains weights on it is called weighted graph, okay, it is called weighted graph. Next, complete graph. Graph with all edges is called complete, meaning from, if I have 4 vertices like this, from this vertex I have 4 vertices A, B, C, D. From this vertex, if I have path to all 3, from B I already have to A, to C, to D. From C I have to A and B, I have to D. From D, like this. From a vertex A, if you are having path to all other vertices, then that kind of a graph is called complete graph. Next, graph with relatively few edges is called sparse graph. With with few of the edges missing is called dense, okay, right. If there are only few edges, it is sparse graph. If there are so many edges, it is called dense graph, right. Directed weighted graphs are called as network. Directed weighted graphs, meaning in this case here, if I have directions something like this, this is called a network, this is called a network, okay, like this, this becomes a network. So, generally we denote vertices by like this and edges by this, this is also fine. Applications of graph, where do we use graph? Graphs are very widely used in transportation problems, in transportation networks, highway network, flight network, for all those things you can represent them as a graph. Even representing relationship between components in electronic circuits, we use graphs, okay. So, computer networks also we use, because LAN, internet, wherever you want you can use this. In database also we use this graph to represent entity relationship diagrams, okay. AR diagrams we use the graph concept to represent them, right. So, these are a few applications of graph. How do you represent a graph? Okay. How do you load a graph into, how do you store a graph data? How do you store a graph data? So, we have seen that a tree can be stored in my computer memory using linked list representation. I can use double linked list to store a tree structure like this. I can store a double linked list in this format, right. So, this is how we store. But how do you store a graph? When you have a graph with you, you have a connected graph like this, how do you store this in your computer memory? So, there are 3 different ways: adjacency matrix, adjacency list and adjacency set, okay. You can store them in 3 different ways. Why we have to store the data? See, to manipulate graphs we need to represent them in some useful form. What is this, each of them? Let us see. Adjacency matrix, okay. So, when you have a graph like this, right, if the graph is directed graph, then we need to mark only one entry. So, this is a graph here. For this, the adjacency, how many vertices are there? A, B, C, D. You write that in column, in the row also you write it same, column and row both you write A, B, C, D. Now, is there any path from A to A? No path, put 0. Is there any path from A to B? Yes, 1. From A to C? No path. From A to D? Yes, you can see there is a path here, direction is given here, right. So, we are having a path. So, this is also 1. From B to A? No. B to B? No self loop. B to C? Yes. B to D? There is no path, no direct path. Like this, you can fill the path between this graph elements. Okay. So, this data of this graph is stored as a matrix form. Okay. It is stored as a matrix form like this, n cross n, where n is number of vertices in that graph, right. This is the most powerful representation of a graph. Graph can be easily stored in a matrix format. Okay. This is very easy to load, very easy to play with that, very easy to perform operations on a matrix, right. The next one is adjacency list. Okay. We have studied something like linked list, right, linked list kind of format. What we are doing here, a node is there A, from there is a path to B, okay. From there is a path to B, and there is a path to D. From A there is a path to B, from A there is a path to D, and from D there is a path to A. So, that way also we can represent. This is not for that graph, but some other graph. From B there is a path to C, and from C there is a path to B. Like this you can represent the adjacency list. We have to use linked list format. Okay. We have to use linked list format. If you see for this, it will be A to B to C, again from A to D, okay. Then again B to C, then that is it from here. Then we have from C to D, C to A is also there, C to A is also there. Then D there is no path. Like this you can store them as a linked list. Okay, you can store them as a linked list. But the problem here is you need lot of memory. You need lot of memory in the adjacency list format to store the graph. That is why the most powerful one is adjacency matrix. We use it very frequently to store them in a tree. In a matrix form we can store that graph, right. So, adjacency set, we have to study disjoint set concepts. Okay. It is a special type of I cannot say a special data structure, but it is a special type of a set, disjoint set. We use that to store adjacency set here, but among all these three, the most powerful is adjacency matrix. So, we will be using adjacency matrix representation to store a graph, and we will be solving problems based on this adjacency matrix only. Okay. So, these are the different ways you can represent the graphs in computer memory. So, these are few basics of graph theory. I could say the introduction of graph theory or graph concepts. What is a cycle, what is a tree, right, degree, subgraph, adjacent vertices, cycle, connected, disconnected components, directed acyclic graph. Okay. We have so many such concepts in graph theory. It is a very big concept, right. So, these are few of them which are sufficient for us to understand our graph theory algorithms which are there in our syllabus. Okay. Right.